All right, we're going to continue looking at the area between intersecting curves. The next thing we want to look at, though, is what happens if they don't give us those limits, and we have to find our intersection. So here's what we're going to do. First thing we're going to do if they don't give us our limits is we're going to find the lower and upper bounds of the interval by finding our points of intersection. So we're basically going to set our two functions equal to each other, because whenever they're equal to each other, they're intersecting. We can determine which function is the lower bound and which is the upper bound. In other words, what's the top curve, what's the bottom curve, just like we did before, either because we have knowledge of the function or because we look at it on our graphing calculator. And then we're just going to compute that area just like we did in the last video. FYI, you might need to do more than one integral and add the areas. We will look at one example like that. There'll be 3 examples total. So looking at the first one, also if you want to have a graphing calculator handy, I am not going to go through the integration process on these. I feel like we've had a lot of practice with the integration process. We just need to figure out how to set that integral up, and then I'm going to use my graphing calculator to actually do the integrating for me. So looking at the first example, I want to find the area bounded by these two curves. First thing I'm going to do is I'm going to figure out where do these curves intersect. So I'm going to go ahead and set the curves equal to one another. When does 2 minus x squared equal x? Well, I'm going to add the x squared and subtract the 2. That is then going to give me 0 equals x squared plus x minus 2. Factoring this, I get 0 equals x plus 2 times x minus 1. Therefore, my limits are x equals 1 and x equals negative 2. So I have an integral from negative 2 up to 1. So now I'm going to do top curve minus bottom curve. So I can either know about what these look like or I can look at them on my graphing calculator. It's going to be something like this. So my parabola is upside down. It's shifted up 2. Y equals x. So I'm going to have a graph that looks something like this. So my top curve is 2 minus x squared. So top curve minus bottom curve gives me the integral from negative 2 to 1. Simplifying this, 2 minus x squared, distributing my minus, it only has to distribute to one term. This I'm going to put into my graphing calculator. Once I do, I get an answer of 4.5. So I found where my curves intersect by setting my equations equal to one another. I determined which was my top curve, which was my bottom curve. I subtracted top curve minus bottom curve. I integrated. Again, I'm just using my calculator on these. Looking at the second example, I'm going to go through the same things. I'm finding the area between y equals sine x and y equals cosine x for one of their intersecting regions. If you think about the sine curve and the cosine curve, they are going to intersect all the times because there's those wave functions that go on and on. So where is one place where they intersect? Well, I'm going to go ahead and say, when does sine x equal cosine x? Well, if I think about it, I'm going to need 2 places always because I have to have a lower limit and an upper limit. So if I think about my unit circle, the very first time these two are equal to one another is at pi over 4. The next time these two functions are equal to each other is at 5 pi over 4. So when I'm integrating, I'm going to start at pi over 4 and go up to 5 pi over 4. Next thing I have to figure out is which is my top curve, which is my bottom curve. I can graph it on my graphing calculator. I'm actually going to go ahead and sketch it out because I'm very familiar with the sine and cosine curves. So pi over 4 I know is just going to be right before pi over 2. Pi. And 5 pi over 4 is going to be right before 3 pi over 2. So they're the midsections of those intervals. So if I graph my sine curve in, say, red, sine starts at 0, goes up to 1, back down to 0, down to negative 1. So here's my sine curve. If I graph my cosine curve, say in green, cosine starts at 1, comes down to 0, down to negative 1. I'm off. Why am I off? Down to negative 1. Oh, yep, back up to 0. I'm not off. Never mind. Going ahead and drawing this curve in. So notice they're intersecting at pi over 4 and at 5 pi over 4. So if I want to find that area in between, notice that my top curve is my sine curve. So my integral is going to be the integral, coming back here again, from pi over 4 to 5 pi over 4 of my sine curve minus my cosine curve. Again, from here, I'm going to go ahead and I'm going to put this into my graphing calculator. It is going to give me an approximation. My approximation is going to be about 2.828, always going to 3 decimals. My exact value, if I were to actually go through the integrating process, is 2 square root of 2. But again, because I feel like we've done so much with the integrating process, I don't think it's worth my time and your time to go through that in the video. Now, if you would like me to go through that with you in class, please let me know and I would love to do that. Looking at the third example, now we're intersecting. What happens when we have more than one intersection point? So what we're going to end up doing is going through the same process with multiple integrals. So let me go ahead and set this up here. Where are these going to intersect? When does 3x cubed minus x squared minus 10x equal negative x squared plus 2x? So working through and solving this, I'm going to move everything over. So I'm going to add the x squared, so my x squareds will cancel. I'm going to subtract the 2x, so I end up with 3x cubed minus 12x equals 0. I can factor out a 3x, giving me x squared minus 4 equals 0. So I know x can be 0, x can be positive 2, and x can be negative 2. So I have intersecting again at more than 2 points. So all I'm going to do is I'm going to set up 2 integrals. So the first thing I would do is I would graph both of these equations to take a look at what they look like. I can pull out my graphing calculator. When I do, and I'm going to go ahead and set my window on my graphing calculator to go from negative 2 up to 2. And so what I notice is that my cube function is going to come up, back down through 0, and ends here. Whereas my quadratic function, I'll put that in a different color, that is going to start here and come up, and then, and then come down to here, and I didn't graph my cubing function correctly. This was actually supposed to come down and then come back up, so ignore that. So notice that from negative 2 to 0, my cubic function is on top, and from 0 to 2, my quadratic function is on top. So setting up 2 separate integrals, I'm going to have my first integral that goes from negative 2 to 0, where my cubed function is on top, so I'll take my cube function minus my quadratic function, negative x squared. I'm going to add to that the area that's underneath my next intersection from 0 to 2, where now I have my quadratic function on top, and subtracting from that my cubic function. So I'm going to go ahead and simplify this. When I do, I get the integral from negative 2 to 0. So let's see, 3x cubed has no like terms. Negative x squared minus a negative x squared, those are gone. Negative 10x minus 2x is minus 12x. Plus the integral from 0 to 2. Negative x squared minus a negative x squared, those are gone. 2x minus a negative 10x is 2x plus 10x, giving me 12x. And then a negative 3x cubed gives me minus 3x cubed. From here, all I'm going to do is put this into my calculator. Again, we've had a ton of practice with integrating. I don't see a reason to use your time to watch me go through this integral process. Please make sure, though, in class, if you want to see where this comes from, that you're touching base with me, or how I put it into my calculator, or how I would do it without a calculator. But putting each of these into my calculator, the first one gives me 12. The second one also gives me 12, giving me a total area of 24 for my 2 integrals.